So let's give everybody a second. All right, sweet. All right, so no screen sharing on live stream. So if somebody's watching live, they're gonna have to use their imagination. But I'm going to talk about Numpy. So this is the beginner's level talk. So I'm just gonna try to give a brief introduction of Numpy and how to use it and some of the functionality there. So the first thing you want to do with Numpy is you probably want to pip install it. So it's usually just a pip install away, pip install Numpy or pip3 or however you have pip set up. You probably want a virtual environment or whatever, but that's out of scope here. So you can just pip install Numpy. And so to import it, usually this is kind of the idiomatic way that you see everybody in the community do it, is import Numpy as np, because it's a lot shorter to type np dot than numpy dot, because programmers are lazy, and I like being lazy, so np is a lot better than typing out Numpy. And so once you import np or Numpy, you have np, so you can get this nice little np object that has all these functions off of it. And so the first thing you want to do is you probably want to create a Numpy array. So the easiest thing you can do is just you have a Python list, and you can just wrap that Python list in np.array, and it will automatically convert it to a Numpy array. And so now you get all the good methods of Numpy. So one of the most basic things, and probably the thing you're going to be doing most often when you're doing Numpy and you're doing calculations, is you want to know the shape of your array. So this tells you like how many rows, basically how many rows in each dimension that you have. So like right now we have like a one-dimensional array with 3 records in it, but we can as easily have a matrix, which is, you think about in rows and columns, and you have 2 rows and 3 columns here. And you can go like n by n dimensional, if you can imagine that. It's kind of crazy to think about in dimensions. But yeah, so this is the basic ways to get going with Numpy. And so those might be the most, intuitive and standard ways that you see people, and at least initially, creating arrays. But you can do all kinds of different things to create Numpy arrays. So you just want an array of a certain shape with zeros, and this might be like if you're starting a machine learning algorithm and you need like a Numpy array in a certain shape of zeros. This is kind of a handy method because it's pretty annoying to have to type all of this out. Like you don't want to have to type this zeros everywhere. So this is nice and handy to have that. The np.random.rand. So this gives you a array of shape, whatever you pass it to. So 4 by 4 in this case, and this gives you values on a scale of 0 to 1, and they're random. So unless you set a seed, they will be different values every time, which different machine learning algorithms or different techniques that you're doing with your array might need a random distribution between 0 and 1. It's kind of a popular thing. You can also do integers. So this one is like this I did 0 to 5, and this gives you size. So this is 2 by 4. So you can do 0 to 10. You can do whatever, and this gives you integers. So that's a nice one to have too. And so once you have a Numpy array, you probably want to see like what is on it. I mean, you could go read the docs, or you can just dir it and see what's there. So you see all these dunder methods. We'll go over how this overrides a bunch of functionality in a minute. You can have like argmin, argmax, all kinds of cool stuff. You can go read the docs and find out more, or you can just call help on them if you are a true Python programmer. So yeah, those are some of the methods you have there. And then one last thing is if you want the identity matrix, you can do np.I, and it gives you the identity matrix 4 by 4 here. And so that's pretty much for creating Numpy arrays. Any questions about any of that? Cool. Yeah.
It's not really an important question, but why do you have the underscore as your suffix on your variables?
I have no idea, because I did this talk in a hurry and I didn't know what to think of to name my variable, so I just put a suffix to make it not as confusing, I guess. Yeah. That's what the identity matrix is. Yes. Yes. The identity matrix is a diagonal of ones in the n by n dimension. So it has to be a square matrix with all the diagonals as one. And so probably one of the other most popular things you're going to do once you first have a matrix is you're going to transpose it, because a lot of the calculations you're going to want to do is you're going to want to shift your array around to get it into the shape to do the calculation that you need to do. And like linear algebra, you always do transpose. Machine learning algorithms, you're always going to want to be transposing your data around to get it in the right shape to do your matrix multiplication or your addition or subtraction or whatever you may be doing for your algorithm. And so there's once you have your matrix and now you can do your basic transpose operation, you might want to get data out of it in certain formats. So you might want to, like, Python list have the slicing syntax, so does Numpy. So say you want the first row, hold on, let me think about this for a second. The second row, because it's 0 index, second row, I've been programming in R too much lately, so my mind is all warped here. So the second row, and then you want 2 elements, so you go and you get 2 and 5 here, like that. You want the 0th column on a NumPy array. So here it gives you the 0th column, and you can get the first column, and it just gives you as a one-dimensional. But if you do the second one, it doesn't exist, right? So that's pretty handy. Is sometimes you just want a column of your data. Yeah. Any questions about that? So now I'm going to go over kind of what makes NumPy powerful and like why even use this. Like you can do, I mean, yeah, the transpose and stuff is nice. You can't really do that with a regular Python array, but you could implement that pretty easily with a helper function. But what makes NumPy a lot more powerful than Python list is everything is vectorized. So for the R programmers out there, this is kind of like the default thing that you just like take for granted, is like all my operations are vectorized. Everything's a vector in R. Well, in Python, unfortunately, that is not the case, but with NumPy, it comes to save the day. So what that means is in regular Python, if you have a regular list and you like divide, you have an array of numbers and you divide it by 2, like it doesn't know what to do with that. With R, it applies the scalar operation across all of the elements of the array. And so that's really powerful because it gives you a lot of efficiencies. So instead of having to operate element by element by element at a time on your array, you can apply an operation, and it's much more efficient. Especially with like modern hardwares have, at the hardware level, you have like SIMD operations that can, you know, really make these operations a lot more efficient than element by element. And there's a lot of other stuff that goes on under the hood that makes these operations a lot more efficient. Like I'll have an example later, and if you do like a vectorized operation versus doing in for loops, it can sometimes be the matter of like 2 seconds versus like 20 minutes. It's really that crazy with some of these operations. And so here it just shows you can divide the whole array or vector or whatever you want to call it by 2, or you can add 2 to each element. And then here shows like how NumPy kind of overrides the operators in Python. So like if you have 2 Python lists and you say, oh, I want to add all these elements together. Well, nope, it just combines the array together. Sometimes that's what you want, but probably not in this case. It's probably not what you want if you're trying to do some math and add stuff together. But NumPy to the rescue. You convert these to NumPy arrays and you add, and it does the element-wise. It knows the shape, going back to the shape, and it knows how to interact with the shape and apply the operations to each element correctly. Same thing with multiplication, and you got to be careful here because multiplication in NumPy, sometimes you want matrix multiplication and you're using the multiplication operator, and this is element-wise multiplication, not matrix multiplication. So I'll show you some different ways you can do matrix multiplication here shortly. But so this just does element-wise multiplication. So like 1 by 4, 5 by 2, 6 by 3. But say you want to do matrix multiplication. So there's kind of 3 different ways you see this done. You see a lot of people do NP dot, and to me this is confusing. I don't really like this syntax. I feel like dot is kind of confusing. I mean, it does the same thing, but to me it's kind of like this really isn't what I don't know. It's just not intuitive to me for me to think about this as a dot product kind of operation. I don't know. Your mileage may vary. So you see here you can do np dot dot on a 2-dimensional, and it does matrix multiplication. So going back to linear algebra, it applies the operations, and you get out so you have your 2 by 3, 2 by 3, and you get your 2 by 2, or yes, whatever that is. I can't explain it while I'm talking, but you know what I mean. So you do mapmul. That's another way. This to me is a little more intuitive. It's like, oh, this is a matrix multiplication. And then you also have this operator, which I like the best, but you really don't see that many people use it. Yeah. 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 You really don't see that many people use it. Like the first time I saw it was a couple weeks ago, honestly, and I was like, what is that even doing? Like, I don't even know what this is doing. And then I was like, oh, that's what this is doing. And now I kind of like it. It's like, okay, this makes sense to me. So yeah, this is kind of the shortest hand of doing the matrix multiplication. And so that shows your basic arithmetic operators and how they're kind of vectorized and the fun stuff you can do with Numpy. Subsetting. So this is kind of like R has this same functionality. So you say you have an array, and like here, I only get the even numbers out of an array, and I want to subset it. So this operation right here will return an array of true and false values, just like R. And basically, this syntax knows, okay, if it's true, keep it. If it's false, drop it. So this is really handy if like you have a vector and you just want to filter out some values really quickly. Okay, so this shows another big powerful feature of NumPy is the axis operator. So sometimes you want to, operate on rows. You want to do like row level operations. Sometimes you want to do column level operations, just depending on your problem. So the axis allows you to do that. And so here you can see NP sum on a row level. Well, it doesn't really do anything because we're not really have any rows to add it to. But here, if I do it on the column, it has, sorry. So never mind, I got confused for a second. So yeah, it does the row level. So it does 1, 4, 2, 5, 3, 6. So it does the row level addition. But if you want to do column level, so say I want to add 1, 2, and 3, that gives me 6. And then if I want to add 4, 5, and 6, that gives me 15. So it's just a little handy method, and you can do like mean, and there's other operations you can supply on a column or row level with using the axis. And so lastly, before I go into too much details, NumPy has some linear algebra operations. So if you ever want to do some linear algebra homework and you're too lazy to actually calculate it yourself because those can get quite tedious, you can just pull out NumPy and it will find your eigenvalues and eigenvectors for you, or you can actually use it to solve a system of equations, which is really nice. So it's got the nice linear algebra operators there for you. So here's a problem that I actually worked on recently. So this goes to show like how you can easily take, this isn't super complicated depending on your level of comfortability with math, but I mean it's fairly, grotesque, I guess you could say, if you're not used to looking at things like this. And this just shows how you can just break this down into NumPy very easily. And it's almost kind of like when you think about this isn't a lot of code, but there's a lot going on in these few lines of code. So, but it just, with the power of NumPy, is you have this like math equation right here, and you can do this whole operation in what is 3 lines of Python code with NumPy. So you have so here, this is a little, so my matrix was already transposed, so I didn't actually need to transpose it again versus what the assumption of this equation was showing. So that's one thing here. But so you just take x and you can map mall it by beta, and then you minus y. And so here, I could write this in a for loop, and I could like do these element-wise operations, but you could try this, and it would take literally 10 times as long. And then you could just map mall it again by xi. And so basically, this NumPy takes care of the summation for you. It just broadcasts all these options, and it does all the summation for you. So all you have to do is, do the 1 over n and multiply it by -1. And you just have this whole nasty derivative that's doing gradient descent calculated for you in a few